Okay. So let us assume that, so if you have 3-level inverter, okay, so 3-level, so diode clamped inverter. So how to do, so with this, in case if you are operating as an active rectifier, okay. Right, so this is a 3-level, so NPC based active rectifiers. So we have source here and 2 DC link capacitors. So we are operating AC to, so we are performing AC to DC conversion in this case, and we have this load here. So some DC load we are connected. So usually this load may be a large DC motor or any other heating element in case of heating application. So all right. So this is the AC source and this is 2 DC link capacitors. So now the controller, so whatever we discussed earlier, so that remains same, right? The controller will be same. So only thing is, so where this difference occurs, so when we are selecting this, when we are controlling this V reference with the actual value of this VDC, okay, this actual load voltage. So what the difference is, right? So earlier you have only one capacitor, right? So you have only one capacitor. So that means you have, this is plus minus, we have this reference, and this is a PI controller, and this is V actual. So that will gives you the I maximum. Okay. So because you have only one capacitor to control, right? So but in this case, you need to control the 2 capacitors. You need to control 2 capacitor, and at the same time, right? So for example, if a reference is 600 volts, the sum of these 2 capacitors must be 600 and their individual must be 300 and 300. So then only it will work properly. It will produce all the levels, right? So it will produce all the levels in the output voltage, that is AC side, and it will maintain the DC voltage at some reference value. Clear? Right? So for in case of 2 capacitors, so what we need to do is, so we need to slightly modify the controller, right? So we need to slightly modify the control, right? So in that case, so what we have to do is, we need to tightly control these 2 capacitor voltages. So that means the sum we need to control to the reference value, and the difference we need to control to 0. Okay, difference must be the sum of these 2 DC link capacitors, so must be equal to the V reference, and the difference of these two must be equal to 0. So that means you require 2 PI controllers. So let us assume that VDC1 is the first capacitor voltage and VDC2 is the second capacitor voltage. The sum of these two, VDC2 is the second capacitor voltage, right? So we have one controller here, one PI controller. So this is V reference, the sum of the 2 actual capacitors that must be maintained. So we have plus here and minus here. So this is VDC1 plus VDC2. So this is the sum of 2 capacitors. So here this is given to one PI controller. So this will generate some output voltage. It may be some current waveform or some current reference, right? Similarly, the difference between these two, so we have another PI controller, right? So that is the difference between these two, VDC1 minus VDC2. Okay, so that you need to compare with 0. You need to compare with 0. So this is plus again, and this is minus again, and the difference you need to give to a PI controller, right? So that will generate, so the difference current error, right? So we need to add this one and 2, right? So we need to add together, so that will gives you the I maximum. So that gives you the I maximum command. Okay, so that is the difference. So rest of the things are same, right? So here the rest of the things are same. So another difference is when you are implementing the modulation scheme. So in that case, we use this triangle carrier, right? If you want, you can use some any level shifted PWM technique. So any PWM technique, so we can use. So that means the other difference, so lies here. So this is the PWM generation, right? So here, this one we can replace with so level shifted PWM technique. So if we have 3-level inverter, okay? So that is, it will generate the modulating signals. So how the modulating signals are generated? So we have this I reference, okay? So we have, this I reference, okay? And this is I actual. This is I reference and this I actual is plus minus, and this you give to a PI controller. So the output of this PI controller so will generate the modulating signal for this level shifted PWM technique. Okay. So you have two changes here. So when you are using a 3-level inverter, the first change is, so this is the first change here. So earlier you have only one capacitor. So now you need to control 2 capacitors, right? The sum will be controlled. The sum will be compared with the entire reference voltage, and the difference is we need to compare with 0, right? So other change, this entire thing is same. The other change is PWM generation. So earlier we have this either we use triangle carrier control PWM scheme or hysteresis controller. So but here, so those methods only applicable for these methods for 2-level. So if you want to use, we can use this PWM techniques, so that is level shifted PWM. So this is how to generate the modulating signal. So this is I actual and this is I reference, right? So this is similar to the triangle carrier. So the modulating signal we are generated, right? In case of 2-level, this is compared with one carrier. So whereas it is compared with 2 level shifted carriers. Okay, so that is the only difference. So rest of the things are same. Okay. Right. So this is how we will control this. In some cases, right? So this is plus minus. This is VDC2 minus VDC1, right? Some other will follow like this also, right? So this is 0. So this is VDC1 minus VDC2, and this is VDC2 minus VDC1, right? So this will gives you the another PI controller, and this will gives you the third one. So that means all three will be added together. Okay. So this is optional. Okay. So this is the third one is generally optional. Whenever you want tighter control of these two DC link capacitors, so we need to follow this one and this one, right? To further reduce any small deviations, we also go for this third one, right? Clear? So however, so how much effort you put to tune this, right? So it will not give you the satisfactory results, right? So it will not gives you the satisfactory results. So whatever the tuning you're trying to do is, right? So it is difficult to tune in all operating conditions. So the best way is to use some additional circuit, so that we discussed, right? So this is the additional circuit. So we need to connect. So we need to connect a switch here. We discussed this, right? And another switch. The sole purpose of these two switch is these switches is to balance these two capacitor voltages. Okay, to balance these two capacitor voltages, you require this kind of arrangement, this kind of external arrangement. So this will balance these two switches. Okay, it's clear. We already discussed how to control these two switches, so that remains same here. Okay, the switch firing signals for this upper and this bottom additional switches, so we already discussed in previous classes, that remain valid here also. So rest of the control is same. Okay, so rest of the control is same. Clear? So this is about, so when you have neutral point clamped or a diode clamped inverter, in case of particularly 3-phase. Okay, so particularly 3-phase. So if you have so for example, if you have 5-level, right? So this is for 5-level case. So we have AC supply here and we have this DC on the other side. So in this case, right, in case of 5 level, so now we have 4 capacitors. So we need to balance these 4 capacitors, right? We need to balance these 4 capacitors. So this particular example, so we have the 6.6 kV. On the other side, you are getting 6 kV positive and 6 kV negative. So that means the total DC link voltage is 12 kV. So the 12 kV DC link voltage you are getting, right? So this 12 kV is shared among these 4 capacitors. So that means each one will be supposed to charge to 2K in this example. Okay. So in this example, the source voltage is 6.6 kV and the DC side you are getting 12 kV. And this is the 5 level inverter. So we are expecting that each capacitor should be charged to 3000 volts. Okay. So in this case, right, so in this case we have 4 capacitors. So whatever we discussed, that means the sum and the difference with separate PI controllers, so that will not appropriately work here, so that we require some extra circuit. Okay, here we require some additional circuit to balance these 2 capacitor voltages. So that circuit will be something like this. Okay, so we have this inductor here and we have one switch here. Okay, and another switch here. There is no inductor here. Here inductor. Okay, so this is the arrangement. You have inductor L here, another L. So this is switches, additional switches S1, so S2, S3, so S4, and we have this DC other side. So that is connected to load. It's clear. So this is how. So we'll proceed with in case of 5 level DC MLI. So the operation is same, right? So to balance these 2 capacitors, right, this one, and to balance these 2 capacitors, so we are operate 2 capacitors. We have this chopper circuit. So this is already discussed that. So this is a 2-quadrant chopper. To balance these 2 capacitors, this bottom 2 capacitors, we have this circuit. Okay, so we already discussed that, right? So whenever we have this additional voltage in any of the capacitors, that additional voltage is transferred to the inductor, right? So first it is transferred to the inductor and later it is transferred to the any bottom any other capacitor, so which is having low voltage. Okay. So that under steady state, so it is expected that all the capacitor voltages will maintain its reference value. So that's how we will control in case of this, right? So here, so everything is same as 3 level. So but the difference is here you require 2 inductors and 2 inductor circuits you require and 4 additional switches. So now the question is, so what is the blocking voltage of the switch S1? So what is the blocking voltage? So for the switch S1. Anyone? So what is the blocking voltage? So for the switch S1.
That's 6K. 6 kV, sir.
No, for okay. So blocking voltage. So how you said 6 kV means that means 2 times the capacitor voltage, right? For example, this switch is off. For example, we are calculating the blocking voltage for this S1, right? Okay. So when this S1, right? So it is connected to this point, right? That means this midpoint is clamped here. Okay. So for example, this S2 is conducting, right? In case of this S2 is conducting, so how much voltage so that appear across this S1? So enter this top 2 capacitors, so that will appear across this switch, right? This switch S1. So therefore it's supposed to block 2 times the VDC. If you assume this is each one is VDC, it's supposed to block 2 times the VDC. Okay. Clear? Similarly here, this one also, right? For the example, this is not conducting and this one is conducting. It's supposed to block 2 times the VDC. So its maximum blocking voltage is 2 times. So this when you are calculating the blocking voltage for this S1, so these two bottom capacitors will not come, right? Because this midpoint, this point is clamped here, right? So that means the voltage is restricted here. Clear? This voltage is restricted. That means the maximum voltage or the voltages that appear, so across this S1 is one is VDC and another, so when S2 is conducting, its voltage is 2 times the VDC. Okay, clear? So we have two options, right? So we are calculating the blocking voltage for this S1, right? So let us assume that the switch S2 is on. The blocking voltage is 2 times the capacitor voltage, 2 times the capacitor voltage. So let us assume that the capacitor, the switch S2 is off. Okay, if this S2 is off, so in that case, the blocking voltage is the sum of these two voltages, inductor voltage plus the capacitor voltage, inductor plus capacitor voltage, right? So the inductor voltage, it may be positive or negative, so depending on the current direction. Okay, clear? This clear, right? So when S1, we are calculating the blocking voltage for S1. So if the switch S2 is off, okay, so in that case, we have these two capacitor voltages, so that is VDC1 plus inductor voltage, so voltage across this inductor. Okay, it may be this voltage across this inductor may be positive or negative, so that all depends on the current direction and how it is charged. So when this S2 is on, so in that case, the blocking voltage of this one is, so that is equal to, so this VDC1 plus this VDC2. Okay, so that means, right, so this switch one is normally diode clamped, right? So we already discussed rating of the switches. So each this switch, this main switches, right? So each switches, so must be rated for VDC. So this switch is rated for VDC, right? This switch is also, all switches are rated for VDC. Okay, so that means, so here this blocking voltage is 2 VDC, so therefore we need to connect two switches in series. We need to actually connect two switches in series like this. Okay, so we need to connect two switches in series. Okay, clear? So this is how this voltage balancing circuit is there for in case of a 5 level. In case of 5 level, so this is how it is designed. Clear? So only thing we need to understand that in that additional circuit, so which the one that is using for this balancing capacitor, so that rating, so we need to just take care. Okay, clear? So next one, so when you are going for cascade H bridge, okay, so this is for cascade H bridge. So next one, if you are using a cascade H bridge, so this is application, so where this is AC is converted to DC. So this is a particular application for the STATCOM. You might have studied STATCOM. So when you're BTech, if you had studied this flexible AC transmission system, you might have studied this STATCOM. All right. So here, so this is in case of particular STATCOM application. So this is connected to a grid here. So this one is connected to a grid. So this grid of 6.6 kV, and we have this STATCOM is connected here. Okay, so we have this we have these capacitors. Okay, so we have these capacitor circuits. Right. We already discussed that. So when STATCOM, right, STATCOM is used to control the reactive power, right? STATCOM is used to control the reactive power so that the power transfer capability of the grid can be increased. So that is the basic thing of STATCOM, right? So it will also control the voltage at particular bus by controlling its reactive power. When the reactive power is controlled, so that the voltage across any particular bus can be maintained some 1 per unit. Okay. So basically transformer, if this is AC side, okay, this is grid and this is STATCOM. So in this case, so normally, ideally, so there is no real power exchange. Okay, so there is no real power exchange, so between the STATCOM and the grid. Okay, there is no real power exchange ideally from these two, right? So because the power that involved, the STATCOM will compensate the reactive power, right? That means the power flow is only reactive power in nature. But, right, so but what will happen? So these are the switching devices, right? So these switching devices having some losses. Okay, so all these switching devices having losses, right? All these switching devices having losses. So these losses are always of real, right? These losses are always of real power. Okay, so losses are always real power, but ideally the STATCOM so will not exchange any real power. So ideally, but it involves some real power that must be, so whatever this real power, so where this real power must be obtained, so usually this real power is obtained by this capacitor. Okay, so that means we assume that, so this capacitor, right, whatever the charge that present in this capacitor, some portion of that one is goes to compensate the losses in the STATCOM, or the switching losses in the STATCOM. Okay, so what will happen? Some losses it is compensating, that means it is drawing some real power. These capacitors are drawing some real power. So what will happen? This capacitor voltage will reduces. This capacitor voltage will reduces. So therefore what will happen? At some point of time, this capacitor voltage is slowly reduces. Okay, so this is not the control requirement. So when you are controlling the STATCOM, so we need to make this capacitor voltage at the recommended value, or that reference value. So then only the STATCOM will work properly, right? So but what will happen? Some of the losses are losses in the switching losses, so that are actually taken from the energy stored in the capacitor. From the capacitor energy, the switching losses are compensating, right? So therefore what we have to do is, okay, so what we need to do is, we need to operate this STATCOM. Okay, so we need to operate this STATCOM, right? So that, right, some of the some real power must be transferred from this grid to, so real power must be transferred, real power must be transferred from this grid to this STATCOM, so that, so whatever the losses that occur in the switches, the switching, all the switching and conduction losses, so that must be compensated, right? So that must be compensated, so that this capacitor will be maintained at their respective values. Okay, right, so you got the point, right? So STATCOMs are ideally designed to transfer the reactive power, but, right, the inverter in the STATCOM produces losses, the switching losses, conduction and switching losses. If these losses are actually, right, if these losses are actually obtained from the capacitor energies, the energy stored in the capacitors, the capacitor voltage will be reduces. Okay, so when the capacitor voltage reduces, the performance will be affected. So therefore we need to provide the controller such that, so whatever the amount of real power, so that are used to compensate, or that are used as a real power, that means that are wasted as a real power uh, due to the conduction of various power electronic switches, so that must be drawn from the grid. That must be that amount of real power must be drawn from the grid, so that this capacitor voltage can be balanced. Okay, so this kind of thing, right, so this is applicable to anything, right? It may be battery energy storage system, or it may be active power filter, or it may be STATCOM, or any application. So for any application, right, so we need to maintain, for example, battery energy storage system. If you are connected a battery here, in case of this one, right, if the losses that are occurring in these power electronic devices that are taken from this capacitor, this battery energy storage system, what will happen? This battery energy, the state of charge of this battery energy will be reduced, right? So that we need to maintain 100% state of charge, we need to draw some real power from the grid. Okay, right? So how the real power actually will flow? We might have studied, right? If this is V these two machines are there. Okay, if this is two buses are there, right? So how the power flow from one bus to other bus will go? So there must be some angle difference. Whenever some angle difference between these two, so in that case, so there will be a power flow actually happen, right? So that is how the power flow will happen, right? You might have studied that power curves. Okay. So whenever there is some angular difference, so how to create this angular difference? Right. So this is AC source. Okay. So this is AC source. So we assumed that, so this inverter, this is actually also an AC source, right? Okay. So this is also a source. So we are trying to operate two sources, right? So this is assume that this is one bus or one voltage, or maybe it we assume that one bus, maybe it is bus one. Let us assume that. So this entire thing, so the terminals that are available, right? So this is bus two. So we must have some real flow from so this bus one to this bus two. So how it will happen? So whenever there is some real power, when angular difference between this bus 1 voltage and bus 2 voltage, so then only the power flow will actually happen, right? Okay, so will actually happen. So why? Because whenever there's some power, we know that, right? Basic equation for the power, you remember? So what is the power equation? What is the power equation?
V1 V2 by X sine delta.
V1, V2 by
V2 by X sine delta.
X sine delta, right? So this is the equation, right? So in this case, so this one is V bus 1, okay? So V bus 2 and some angle, and this X, so this X is basically this LX, so that is XS. Or in other words, so it's L times the omega S, okay? Or LS into omega. Clear? Is clear? So that means this inductor is necessary, right? So to have a power flow, so this inductor is necessary. So this inductor is acts as this line inductance in case of transmission lines. Okay, so that means we need to control this delta, right? We need to control this angle so that there will be power flow between these two converters. Clear? So this is the basic thing for STATCOM. So later classes will go more onto this. Okay. So now, before that, so I will give you an example. So how to design this CHB, this cascade H bridge inverter. So for any application. Okay. So let us assume that this is the same example I will consider. So let us assume that I'm designing it for a 6.6 kV. I'm designing it for a 6.6 kV grid. So this nothing is given, right? So that means it is a line voltage. Okay, so this one is the line voltage. So what should be the phase voltage? So it is 6.6 kV. So divide by √3. So that will be the phase voltage. Okay, so that means in case of this cascade H bridge inverter, the phase voltage will be measured between this point and this point, right? The phase voltage is usually measured between these 2 points. Okay, so that means ideally, right? So ideally, if you measure the voltage between this one and this one, it's supposed to be 6.6 kV by √3. Okay, it's supposed to be or approximately near to the 6.6 kV by √3. Clear? It's clear? Right. So this can be designed in 2 different ways. Okay, so one is, so first we'll select the DC bus voltage or DC voltage of each source. That means we'll select this one first, right? So we will select this one first. So based on that, right? So based on that, so we will select the number of H bridges that we actually require. So that means we'll select the VDC first, each capacitor or each bridge DC side voltage first. So based on that, we will select the N, that is cascade number. So that means how many units. So we are supposed to use supposed to cascade. So that will select. This is one way. The another way is, so first we will select this N. Okay, so first we'll select this cascade number. So how many H bridges we need to connect. So based on that, so we select this VDC, right? So based on that, so we can select VDC, right? So before that, right, so all these H bridges, whatever all these H bridges, right, all these H bridges are operating in PWM mode, right? So all these H bridges are operating in PWM mode, right? So but as a rule of thumb, right? So if you give 1000 volts, if you give 1000 volts on the DC side, if you give 1000 volts on the DC side, you are operating this H bridge inverter in unipolar mode. So you will obtain 265 volts, 265 volts on AC RMS voltage. Clear? AC side RMS voltage. So that is 625. So you will get 625 voltage. Clear? It's clear?
Yes, sir.
So that means, right? So that means for the same example, I selected 1000 volts for this each DC source, right? I selected 1000 for each DC source. So how many cascade units you require? So that can be calculated as 6.6 kV or 6.6 or 6600 by root 3 into 625. So how much this value? How much it is? How much this value?
6 approximately.
It is approximately, I think, I remember 6.1 or something you'll get, right?
Yes, sir, 6.1.
Yeah, 6.1, right? So that means it's supposed to be 6. Okay, the nearest value is 6. So we may consider 6. Right? If it is 6.1, 6.23, something like that, right? You may go for 6. Or if it is 6.7, 6.8, if the answer is 6.7, 6.8 or 6.7, 6.9, so you may go for 7. Okay, or selecting the 6 and 7, so that all depends on the available switch, that is right. Okay, so that means if you select 1000 volts, right, if you select 1000 volts for each DC source, so in that case you will get, or you will get, means you need to cascade 6 H bridges in cascade, right? 6 H bridges in cascade. If this switch is 1000 volts, right, if the switch is 1000 volts, so we need, next step is to, we need to see the manufacturer data and what should be the available switch we have, right? If this is 1000 volts, so we usually consider a factor of safety, so 1.6 to 2 times, right? 1.6 to 2 times factor of safety. So that means the switch must withstand at least 1.6 times 1.6 kV, right? The available switch must withstand 1.6 kV, right? So if we consider this manufacturers, we have the 600 volt switch there, 1 kV switches are there, 1.2 kV switches are there, 1.7 kV switches are there, 2.3 kV and 4.5 kV switches are there, and 6.6 kV switches are there, right? So based on that, so what is the best switch we can consider is this 1.7, sorry. So the best switch we can consider is 1.7 kV. Okay, clear? So if we select 1000 volts is the DC voltage of each capacitor or each DC source, so we need to select a switch rating of 1.7 kV. And so how many such switches are required? So it is 4, each H bridge we require 4, right? Into number of H bridges that are in cascade, so that is 6, into, so for 3 phases, so this much of switches you actually require, that means around 72 switches you actually required. Clear? So this is how to design for 6.6 kV per, right? So the other way you can fix this N, right? You can fix this N. You can also calculate the value of this VDC. So only thing you need to remember is for 1000 volts VDC, if the voltage is 1000, if it is operating in unipolar PWM mode, right? So the approximate output voltage on the AC side you get RMS value of this AC side is 625. Okay. So based on that, so we can complete the rest. Clear? So next one is, right, so once you decide this, how to balance these capacitor voltages, how to balance these capacitor voltages in case of cascade H bridge. If you consider this one is the example, so how many capacitors you have? This 1 2 3, right? 6 into 3, so total you have, so 18 capacitors you have, right? So you need to balance these 18 capacitors. So you need to balance these 18 capacitors. So for example, in this case, this is another example for active rectifier example, right? The earlier one is for STATCOM example. This is active rectifier. So this is, you have these 3 DC sources. So we need to balance. You have 3 here, another 3 capacitors, another 3 capacitors. So total we need to balance, so 9 capacitors. Okay, we need to balance these 9 capacitors. So one of the good thing with this cascade H bridge inverter, if you use a PWM techniques like phase shifted PWM, right, phase shifted PWM or carrier rotation based PWM, so natural balancing of these capacitors can be obtained, right, by using this phase shifted PWM or this carrier rotation PWM. So you don't need to do much effort to balance these. So a natural balancing can be obtained. It's a minimal effort, so the balancing can be obtained. So however, to determine the exact amount of this real power, you must require a controller. So that controller that used for CHB to balance this capacitor, it actually consists of 2 parts. So one is cluster voltage balancing, and individual voltage balancing. So one is the cluster voltage balancing and individual voltage balancing. In some of the papers, this cluster voltage is also known as leg voltage balance, and individual voltage and individual capacitor voltage balance, right? Clear? So in case we will go for this first thing, so this individual voltage balancing, right? So in case of individual balancing, so what we had, first we'll go for this cluster balancing, that will be better. So in case of this cluster voltage balancing, so this each phase leg, right? So we have this A phase, B phase, C phase, right? So each phase leg, so we assumed as one cluster. So that means this is A phase cluster, so this is B phase cluster, and this is C phase cluster. So this entire thing is a cluster, so also known as phase leg. Okay, so this is also known as phase leg. Clear? So in case of this, right, in case of this cluster voltage balancing, in case of this cluster voltage balancing, so let us assume that this is VDC1, so VDC, I think this example is fine. Okay, in case of this cluster voltage balancing, so let us assume that this is VDC1, so VDC2 and VDC3, right? So VDC1 plus VDC2 plus VDC3. Okay, So these three voltages, the sum of this A phase, all the voltages, whatever we have, right? So these are compared with V reference into this N. Okay, so this is the individual capacitor, each capacitor voltage, this N is the cascade number. Okay, that means the number of capacitor voltages, so that actually we used. Clear? So this is given to a PI controller. So this will gives you either this current component or the power component, so that use it to balance this capacitor. If the output of this PI, it may be in the form of a current or it may be form of a power, right? So this is for A phase. Similarly for B phase, you have another controller, another cluster voltage controller for B phase, another control for the C phase. Clear? It's clear. So we have A phase, all the capacitor voltages we are added together, and so that is controlled by its actual reference voltage into this N, each capacitor reference voltage into number of HPs, so that are connected in cascade. So this is about the cluster voltage balancing. So whatever this A phase, B phase, C phase, right? So this A phase, B phase and C phase, we have this PI controller is there, right? So this is the C phase, A phase, B phase, C phase controller. We already told that. So this is in the form of a voltage. Sorry, this is in the form of a current form. The output maybe you can assume that it is the current form, or it may be in the form of a power. Okay, right. So remember, if it is in the current form, right? If it is in the current form, so we need to actually deal this separately. So that is A phase, B phase is separate one, and C phase it is separate one. So because if it is in the current form, so that means there is just some phase angle difference between this A phase, B phase and C phase, right? If it is in the current form, so there is just a phase angle difference between this A phase, B phase and C phase. If we assume that the controller, the other controller that we actually use, that we will discuss in the next class, if it is in the power form, if you assume that it is in the power form, or if you assume that this PI controller output is in the power, so that we can add all this together. That means each cluster voltage, whatever this A phase, B phase, C phase, you're actually obtained, right? So that you can add together. Okay, clear? Right? If you assume that it is in the current nature for the another circuit, right? So all these things we need to give to another current controller, right? So if it is assumed that it is in the form of current form, so we do not add all these outputs of this PI controller. If it is in the power form, we need to add all together, right? So this is the cluster voltage balancing. Similarly, we have this individual voltage balancing. In case of individual voltage balancing, so if you consider this A phase, so this is VC1 is the A phase voltage, right? So this is the actual voltage. So VC2 is the A phase, another this one VC3, right? So all these capacitor voltages, so we give to a PI controller, this gives to another PI controller, and this gives to another PI controller, and outputs of all these, so we are added together. Okay, so the reference for this one is, right, the reference, so for this one is usually this V reference. Okay, the reference for all these is V reference. Clear? In case of cluster voltage balancing, so we will add all the capacitor voltages and we will compare with its concerned reference value. In case of this individual voltage balancing, we will consider each capacitor voltage, and after that we have this PI controller. So we have this PI controller, so that gives you to this V reference. That means this is compared to this V reference. So either we will compare this V reference, or, right, this is usually this V reference, or we have this 9 capacitors, right? In this example, we have this 9 capacitor, or the average of these 9 capacitors. Okay, so this may be equal to this V reference, or it is maybe equal to the average of these 9 capacitors. This individual control, we have this for A phase, one controller, similar controller for B phase, and similar controller for C phase. It's clear? It's clear. So it is, in case of cluster voltage control, we'll control each cluster or each phase leg with one PI controller. In case of individual controller, so each capacitor voltage is sensed and it is compared with its reference voltage and it is given to a PI controller. So in case of individual controller, so the reference may be, right, that is obtained the actual reference, or the reference we may consider as an average of 9 whatever the capacitor, the entire capacitors, A phase, B phase, C phase, average value of all the capacitors. Okay, so usually this cluster voltage is the outer controller, and this one, right, this individual will be the inner controller. Okay, so another thing we need to remember, if it is in the current form, so we need to control each phase separately. That means A phase, B phase, will not mix A phase, B phase and C phase. If it is in the power form, we can mix all, right? A phase, individual, E phase. In case of cluster, individual also, we can mix all the powers, right? We can mix all these powers. Clear?
Sir,
Yeah.
how can we know that output of PI controller is current or power?
That all depends on the other controller we have. Okay. Like so like this. Okay, we'll discuss in next class mostly, right? So this is the output, right? Okay, so this so far we are not discussed this, right? So this is what we are right now, we are discussing only this one. So we have one capacitor here, then one voltage, and this is the voltage. So we assume that this output is in the current form. We assume that this is ID star. So this ID star is actually going here, right? So this is actually going here. Okay, so this is the assumption. So if it is in the power form or it is in the current form, so that all depends on the other this is actual controller, so that is employed, right? So this is just additional control, right? The objective of this controller, this individual capacitor or this cluster voltage balancing, the objective is to just control the capacitor voltages. Okay, clear? So how it will depend on, so that all depends on the other control that we employ to control the currents. Clear?
Sir, how do you said that individual voltage balancing is suitable for inner controller and clustering one is suitable for outer controller?
This is usually inner, right? Okay, so whenever this is this outer, right? Because this is, we are controlling all together, right? So if any changes in this inner one, so obviously this will affect this outer one. So therefore, visually we assume that this is the outer controller and this is the inner controller. So you have any doubts on this? So this is an example for a cascade edge bridge inverter. So when you have battery energy storage system, okay, so when you have this battery energy storage system, this is same, right? So this is same. The additional thing is, so we have this additional circuit. So when you have battery energy storage system, so we have additional circuit. So depending on the real power, when you have this battery energy storage system, so we have both real and reactive power. So both can be controlled. Okay. So here the objective is to charge this battery depending on their, right, depending on the state of charge, we can actually feed the power or we can extract the power. So whenever some requirement is there, the power flow is from this battery to this grid. Okay, whenever there's some frequency fluctuations or generally this battery energy storage system that will provide the real power, you might have aware of this, right? So whenever some voltage disturbance is there or voltage magnitude disturbance is there, so the main cause for this one is the reactive power. If some frequency disturbance is there, so the main cause it may be for a real power. Okay, so reactive power will vary the magnitude of the voltage in case, right? If there is some fluctuations in the real power, the frequency will be varied, right? So that additional frequency usually provide this battery energy storage system so that the grid will be unstable. Okay. So we will discuss these things in the next class. Before that, we need to discuss this. Next class, we will discuss this decoupled controller so that you can get a complete picture of all this. So this decoupled controller, so it is used to control the grid active and reactive power control. So it is used to control the grid active and reactive power control. Means, for example, if you are connecting a solar system or some solar PV system to a grid, right? So you actually need to control so how much amount of active power and how much amount of reactive power actually I'm injecting to the grid. So that all depends on this controller. So there are several controllers are there. So one of the most commonly used is decoupled control. So where you can individually control the active and reactive powers. So we'll discuss that in the next class. So you have any doubts on? So you have any doubts on this? You have any doubts? If you have no doubts, I will stop here. You have no doubts, right?
No, sir.
Okay, I'll stop here.